everyone, and welcome to another FLAN Talk. Today we have Jenny Kunz presenting, a PhD student at Linguistic University, working on interpretability and explainable NLP. And today she is presenting to us her paper on where does linguistic information emerge in neural language models. Thank you for being here today, and you can take it from here, Jenny.
Yeah, thank you so much for inviting me. As Lena already said, I am a PhD student at Linguistic University in Sweden. My background is in computer science and language technology, and I work on interpreting and explaining NLP models, pre-trained language representations such as BERT or GPT or whatever. In the first part of my PhD, I worked mostly on probing, which this talk will also be about, and that's asks the question, what linguistic structures and information do self-supervised models encode in their hidden representations? And now I have moved a bit towards self-rationalizing models, asking the question, what insights model-generated explanations can give us into their decision process, and how we can know if this is a faithful explanation. And I don't work on formal languages, but I think it's a really exciting field of research, and I thought that it's still cool to present my work to you, and to maybe discuss with you what relations there may be. But so far I work from an empirical perspective. And to argue a bit for that there is a relation, I would I'd like to say a few words about one of the papers that introduced the probing methodology that I am using. And this paper asks if neural networks can process the hierarchical compositional semantics of natural language, and to isolate this mechanism from other properties of natural language. You see a few here, like ambiguities, irregular paradigms, multi-word expressions, and so on. They use nested arithmetic expressions to investigate this phenomenon, and they did it with very restricted vocabulary, like just -10 to 10 as the numbers they are using. So this wasn't about calculations, but just about in which order does the network process the nested arithmetic expressions, and the calculations can just be remembered because the vocabulary is so restricted. And they looked at this with three different architectures, with recursive neural networks, which can do this nested structure quite by default, and then simple recurrent neural networks as proposed by Ellman, and gated recurrent units. And if you look at this small plot, you see that if you train these networks on this problem, then the three RNNs have the smallest error. So on the x-axis, you see how many numbers there are in this expression. So from 1 to 9, and the tree RNN, or recursive neural network, it generalizes best to all levels of expressions, while the GRU is a bit worse and the simple RNN is worse. And now Kunz et al. Want to know how the networks represent, or how they do this task of solving the nested arithmetic expressions. And it's easy to see how this works for the recursive neural network, but how do the RNN and the GRU do this? And what they use is now also the method that I am using, that's diagnostic classification based on the hidden representation. It's the same what I call probing. There were just a few papers proposing this at the same time. So this is a bit like used in parallel, diagnostic classification and probing. And in particular, they want to know if the RNNs are using a cumulative or a recursive strategy to solve this task. And they look at if the values that are required for the cumulative strategy can be predicted better from the hidden representation. That is, the intermediate value of the expression up to the point where we are right now, or if the recursive strategy values, so as for example, the value within the current brackets, if that can be better predicted. And the finding of their paper is that the RNN models roughly follow the cumulative strategy. And this is a really cool paper. I really recommend reading it. It also has some other nice findings. I will move to a more general level now. So what are these diagnostic classifiers or probing classifiers that Kunz et al. Proposed and that I am also working with? And they work on continuous vector representations, often at word level. And you take these representations and to train a supervised classifier on a diagnostic task. And you can have all sorts of tasks. Examples for word level tasks are part of speech tagging, tasks with syntactic dependencies, semantic rows, co-referent entity mentions, and so on. And you create a data set where you have the representation of the language model from, for example, from some hidden layer as the input, and the gold standard label as the target. And then you use this classifier to, for example, to compare the task performance to a baseline or across layers. In this example plot, you see some example task where you have a worse performance in the first layers, but if you take representations from higher layers of this 12-layered model, then the diagnostic classifier gets a higher accuracy. So this intuitively is then where you assume this linguistic information necessary to solve this diagnostic task is best found in the model, or which is for example, the layer that specializes in information that is useful for this task. And typical findings from the probing literature are that linguistic information is in fact structured hierarchically within the models. For example, one paper from Levens et al. Found that there is a soft hierarchy of tasks, that the first layers perform best at pos tagging, and that for syntactic parents, there you need to go a bit higher in the model to reach better performance. And if you go to syntactic grandparents, like the head of the syntactic head, then you need even higher layers. So yeah, there is some kind of hierarchy in the model. And then Peters et al., who introduced the Elmo model, which was famous for a short time, they also found that pos tags are better predicted from the first hidden layers. So this was had just 2 hidden layers. So kind of small model for today's idea, but yeah, pos tags were better predicted from the first, and word senses better from the second hidden layer of their Elmo model. And then probably most famously, Tenney et al. Found an ordering of tasks that resembles a classical NLP pipeline, where the center of gravity for the pos tags are followed by syntactic dependencies, then named entities, then semantic roles, and then co-reference. So if you would build a pipeline where you use information from lower level tasks for higher level tasks, that would be how you build it. And they found that the BERT model is maybe organized in a similar way, if you can say it like that. And this is of course, you need to be a bit careful with these experimental papers on how to formulate it. And yeah, there is some discussion about the methods, about the methodology and design of probing classifiers. And yeah, particularly how you make sure that the probe really indicates what information is in the representation and doesn't just learn or memorize the task from scratch. And the simplest solution is, of course, to use a baseline, like a randomly initialized vector or the embedding layer. And yeah, then some people argued for simpler and some for more expressive models as the probing classifier. And there have been a few papers introducing alternative metrics or framings of this whole probing enterprise. But yeah, in this field is also this paper that I agreed to introduce here. And we also introduce a metric to evaluate it. And what we do is to measure what we call the emergent information. And the question we ask here is, what if we focus on where in the network information emerges instead of looking at the overall performance? For example, the accuracy of the probing classifier in a layer. And we built on work by Hewitt et al., who introduced conditional probing. they condition the metric is conditioned on the baseline representation in order to explicitly get the information that's in the representation, but not already in the baseline. So they have Li, the representation of the current of, for example, the word in the current layer, and the baseline representation, and they concatenate the two, and then they subtract the accuracy of the baseline. And the interpretation of this is the difference of usable information beyond the prior information that is already contained in the baseline. And yeah, we now use this idea, and instead of a global baseline, we always take the previous layer as our baseline representation in this formula. So we concatenate the current layer Li not with a global baseline, but with Li minus 1. And from this, we subtract the accuracy using only the layer Li minus 1, so that we get, intuitively, we get the information that we have now in our current layer, but that wasn't already present in the previous layer. And yeah, we take the relative information gain in order to be able to compare the results across tasks, even if they have strong differences in the accuracy. And to make experiments with this metric and see what it can tell us, we used 7 monolingual bird models in different languages, and yeah, it's English, Czech, Finnish, German, Hebrew, Swedish, and Turkish that we used. And we take 2 pairs of linguistic tasks that are structurally equal to compare if the hierarchies that we expect to be in the model hold. And to say something very general about the findings, the contributions are generally highest in the early layers. You see in this graphic, at first, the metric introduced by Hewitt et al. With the global baseline, and there the concentration, the highest concentration of information is found in the middle layers for this task. It doesn't matter at this point what this task is, because it looks similar for all tasks. Well, in the latter 2 lines here, local, we see that the local metrics are maximized in the very first layer. So yeah, the earlier the layer, the more important the local contribution of this layer is. So even though you have most overall information in the middle layers, the very first layers are have a far more important gain, far higher gain.
Are you controlling for the fact that the lowest layers might be the most, and might have the most sort of divergence, let's say isometric sort of divergent, that the representations would be most diverged, so it might be more usable in this kind of probe? compared to maybe upper layers where it starts to where individual words will be more similar potentially?
I am not using controls for this, but yeah, of course, what you're saying is kind of explaining this phenomenon that higher layers then perform worse at the lower level tasks, I guess, where you operate more on the word level. So yeah, I don't know how what would be an example where you control for this. Is there?
I guess I'm thinking of like how for for sort of classic probes you have this situation where it's hard to beat random baselines for like unigram tagging tasks that don't rely that much on contexts because because the representations of individual words are just more separated in that space.
Yeah, yeah, I'm not controlling for this that part. It's also, I guess, what's explaining the results, or what maybe the interesting part is at finding out what these differences are. Yeah, I mean, yeah, here in the first layer, that's basically compared to the non-contextualized, yeah, the embedding layer. And yeah, of course, it's kind of intuitive that most information is added where you first see context. So I would say that results aren't surprising in this sense.
I guess, okay, I guess maybe I can ask a more specific question. Do you use something like Hewitt's selectivity baseline to check whether what's happening is about the differentiation of the of unigram representations rather than the underlying structure being used?
Oh, yeah, right. No, I am not using this, or in this paper we haven't used anything like this. But yeah,
Okay,
I
thanks.
would guess that it's kind of, yeah, foreseeable what would happen in line with previous research on this. That, yeah, the earlier the layer, the more unambiguous, of course, you have this unigram representation. Or do you think that something else could happen here?
Well, I mean, the question is whether the the differentiation of the representations accounts for all of the this like detecting of structure in the lower layers, or whether it's still like whether the structure is sort of encoded in some meaningful way, like in there, just by using something like selectivity as a baseline that wouldn't you like that would control for like a lack of real like linguistic structure being used. That would like check that. That's all I'm asking.
Yeah,
like a baseline.
Yeah, I think yeah, I guess you're right about this, that this would maybe bring up something
Yeah, I don't know
interesting.
if it's
I
the
mean,
case.
yeah,
I don't know.
I
That's,
would
yeah.
my intuition would maybe be that, yeah, because the baseline for like the first of these fields is the uncontextualized representations, the network shouldn't, like in the next layers, add information that leads to, yeah, a lower selective probe, but it could, of course, still be. I would guess that the uncontextualized layer would be best to remember. But yeah, yeah, that would maybe actually be an interesting extra experiment.
Okay, thanks. Yeah.
Yeah, maybe we can also come back to this, because yeah, I guess discussing methodology is the whole point of it. Yeah, I will now move to a bit more specific results before we go on with the general discussion. And as I said, we have two pairs of tasks that are structurally equal within each other, and are therefore, as we argue, suited to compare if expected hierarchies hold in the local results as well. And the first one is part of speech tagging, and we compare two sets. One is where we predict where we only use the word tag combinations, where the part of speech tag is the most common for this particular word form. So yeah, and the second one is part of speech tags that are not the most common for a word form. So in the first group, the part of speech tag can be predicted from the word form alone, and in the second one, we have those that can't, that actually require context because of just a word level statistics. It's not possible to correctly predict it, which may maybe come back to this selectivity criterion that Naomi asked for. So the first one can just be remembered by the classifier, and the second one is text where you need context. And yeah, the hypothesis that we now have for the hierarchical ordering of these tasks within the model is that models learn to predict the non-most frequent tags in deeper layers than the most frequent tags.
Oh, hi. I'm just going to say that this actually directly addresses the thing that I was asking about before, about like something equivalent to selectivity. I think this is
yeah, but this is of course only for the one task, and yeah, not directly measuring it. So yeah, it's I think it's still nothing that we addressed conclusively in this paper. So yeah, and yeah, you can see the plots here. For the left one is the global matrix as Hewitt et al. Proposed, and the right one is the local matrix for this paper. And what you see here in green is the non-most frequent tags. What you see in orange is the most frequent tags, and the blue one is both according to the distribution in the data. And yeah, what you see here, the non-most frequent tags, there is generally much more information added compared to the baseline, which, of course, is obvious. Because, the most frequent tags, they can be predicted from word form alone. So for most words, the probe can predict this without contextual information. But of course, there may be some words that haven't been in the training data and where some context helps. So these most frequent tags are still going up a bit, but not too much. There's a bit added everywhere. But the non-most frequent tags, they are better predicted in the middle later layers. You see, if you look at the local metrics, you see it quite explicitly that getting from uncontextualized layer 0 to layer 1, it's a huge jump because apparently if you get some context, then it's already helps quite a lot, and then it's a linear decrease up to a certain point. And but these results are not consistent across the models and languages we are using. And we are quite careful with drawing conclusions about this because the models, of course, aren't comparable in the training data that they use. And for some models, we don't even know all details about if they completely followed original bird's training regime or if they maybe left out one of the pre-training tasks, the next sentence prediction. So this is not something that we can tell much about at this point, but it's certainly something that would be interesting to look into more on how it happens that sometimes models follow this structure and sometimes they don't. And for the second pair of tasks, I have an example with several languages, but let's first introduce the task. It's the prediction of the linear position of the syntactic dependency syntactic dependency head or the parent. So if you have the syntactic dependency tree, that's we predict the head token of a word. And the second task in this pair of tasks is the syntactic grandparent. So if you get the head and then go back to the head's head, that's what we call the grandparent. And we assume, like in line with results by Kunz et al. That I mentioned, that the models learn to predict grandparents in deeper layers than parents, also because, you may need more context, more complex context to predict the grandparent than the parent, because the relation is just less close. But an interesting thing here was also how differently the models behaved. So sometimes we have this expected hierarchy that the parent is predicted the information is added much earlier. Like here in the left plot, you see the example for the Finnish bird model. And here we have most information added in layer 2 and for the parent, but for the grandparent, it's actually layer 3. So yeah, this is the result we expected. There is a hierarchy, but for the Turkish model, we see that, yeah, both peak in layer 3 and follow, yeah, or yeah, the curve just looks similar. So, and yeah, the models were kind of divided between the two patterns. And again, we don't see that we can draw conclusions how this relates to properties of the language or of the training data or training regime of the model or whatever. So that would require more, and I guess more controlled results, maybe with parallel data for the pre-training of the models to see, is it maybe the language itself? Yeah, that would be interesting to do, but yeah, we haven't looked into this yet. But yeah, what conclusions did we draw from this paper? Yeah, it's the early layers where most information either emerges or becomes accessible. And we have a massive dominance of the first two contextualized layers that raises questions about how high level or low level the information that contributes the most to the most overall performance is. Most examples appear to be predicted with rather shallow information, but yeah, I guess it's the others that are the most interesting to look at. And then yeah, if there is a hierarchy of tasks, as we would expect, depends on yeah, the focus on yeah, global usable information. And it is already weaker if we compare Hewitt et al.'s metric with a standard accuracy. So yeah, it's quite sensitive to the metrics if you observe expected hierarchies or not. And yeah, also results are not stable across bird models in different languages, but we don't know if it's little languages or something else that is causing this instability. And yeah, I guess we will have a short discussion now, and I have put some question in the slides here that I would be interested in discussing, like if you have used probing or similar techniques in the context of formal languages, and if you could imagine use cases, or yeah, if you see something in the other direction, like how formal languages can help to develop or verify probing techniques. Yeah, that's what I am interested in, but of course you can also bring up points that you have thought of during my talk.